Today topic of discussion is particle in a box. This topic basically is for engineering physics student and defined very simply in quantum mechanics. Particle in a box is what? For this we can consider that, and we also know about the atom. This is a simple case, and I am considering here hydrogen atom 1H1. This is nucleus, one proton, and this is plus ZD, and this one is electron. Electron is revolving around the nucleus in the 1s orbit. Basically, instead of using this picture, we can make one more picture equivalent to this, and here we can assume that this electron is inside a potential well, or simply well. This picture is equivalent to like this one. Now this electron is into this well, and here we are considering this well one dimensional along the x-axis. So this dimension of the well is x is equal to 0 to x is equal to L, and this is our electron. At x is equal to 0 and x is equal to L, these two vertical lines indicate to the potential. Potential is infinite at x is equal to 0 and at x is equal to L. So these both are basically equivalent to the infinite potential well, and particle is inside the well, and this particle is free to move here and there. Now what we have to do, we have to find out the energy of this particle and the wave function E and psi, and we have to extend this concept for the any state. Energy of the any state n is equal to 1, 2, 3, 4 and so on. N is equal to 1 correspond to the ground state energy, n is equal to 2 correspond to the first excited state, n is equal to 3 correspond to the second excited state, and similarly psi n. Wave function correspond to the ground state, first excited state and second excited state. So we are finding out here the eigenvalue of this particle and the wave function with the help of Schrodinger equation. As we know, the Schrodinger equation H psi is equal to E psi. This is known as Schrodinger equation. H psi is equal to E psi, where H is the Hamiltonian operator. H is the Hamiltonian operator, that is basically total energy. H is equal to P square upon 2m plus potential energy. So H is basically is the total energy, P square upon 2m is the kinetic energy plus potential energy. Kinetic energy plus potential energy, sum of these two energy is the Hamiltonian, that is correspond to the total energy. Now we know about the simplest case, and instead of the simplest case we are considering a particle in a box or a particle in a infinite potential well, and this is one dimensional. So this is one dimensional potential well. The particle in a one dimensional box. Now we have to basically check the boundary conditions. What are the boundary conditions? Boundary conditions is boundary conditions are at x is equal to 0, at x is equal to L. These are two boundary conditions. So we know that particle exists in between these two vertical lines. These vertical lines are correspond to the potential barrier, and this is infinite. So there is no any probability to find this particle electron at x is equal to 0 and x is equal to L. Hence there is no wave function at x is equal to 0 and at x is equal to L, and potential is 0 inside the well. So V is equal to 0 for when x is less than or equal to L and greater than 0, and this potential is infinite at for x less than 0 and x greater than L. It means this potential is infinite if x less than 0 and x is greater than L, and there is no chance to found the particle. So now we have to use this boundary condition in the Schrodinger wave equation, time independent Schrodinger equation. Now the time independent Schrodinger equation. First we have to write the Schrodinger equation for a particle, that is d2 psi upon dx square plus m upon h cross square e minus v psi is equal to 0. This is Schrodinger equation, time independent Schrodinger equation, and we know that v is equal to 0, v is equal to 0 inside the well. So for a free particle, the above equation becomes d2 psi upon dx square plus 2m upon h cross square e psi is equal to 0, because this term will be equal to 0 for a free particle v is equal to 0. So you have this d2 psi upon dx square plus 2me upon h cross square psi is equal to 0. And here we can assume that k square is equal to this factor 2me h cross square 2me upon h cross square. So now the suppose this is our first equation and this is second. So now this equation first becomes like this one, d2 psi upon dx square plus k square psi is equal to 0. Now it is clear that this is a second order differential equation, d2 psi upon dx square plus k square psi is equal to 0. So now we have to find out the solution of this second order differential equation, and we can assume the solution of this differential equation is suppose psi x is equal to psi is a function of x is equal to a sin kx plus b cos kx. Now suppose this is equation number 4, where a and b are the constant and the values of a and b can be determined by applying the boundary condition x is equal to 0 and at x is equal to L. Since this particle cannot penetrate the walls and cannot exist outside the box here and there, the probability of finding the particle will be 0 outside the box, and hence using the boundary condition why we are using this boundary condition? We are using this boundary condition just for finding out the values of these constant a and b, and we know that beyond x is equal to 0 and x is equal to L, the probability of finding of the particle is 0. So using the boundary condition, when psi is equal to 0 at x is equal to 0 and also psi is equal to 0 at x is equal to L. So these are the boundary condition. Now we have to apply one by one into the equation number 4. This is our equation number 4. So we have to apply this boundary condition here. So applying the boundary condition, first boundary condition is psi is equal to 0 at x is equal to 0. So the equation number 4, that is psi x function of x is equal to a sin kx plus b cos kx. This is our equation, and this one is the boundary condition. So psi x is equal to 0 is equal to a sin kx sin 0 because x is 0 plus b cos kx cos 0. So from this equation we can conclude that the sum of these two terms, this one and this one, is equal to 0. Here sin 0 is equal to 0. It means this a could not be 0. Here cos 0 is equal to 1. It means b is equal to 0. So the sum of these total two terms will be 0. So now we can conclude from here that b is equal to 0. Now applying the secondary boundary condition, when x is equal to L, at that time psi is equal to 0 at x is equal to L, and hence the wave function becomes 0 a sin k L. And one more thing here, we can write if b is equal to 0, it means if this constant is equal to 0, it means psi x is equal to a sin kx. So you can conclude here one more thing, that is psi x is equal to a sin kx, where b, this constant, is 0. It means second term is equal to 0 always. Now this is the secondary boundary condition, and we are getting this condition a sin kl is equal to 0, and this condition will satisfy only when a sin kl is equal to sin kl. A could not be 0, is equal to 0. It means sin kl is equal to 0, and hence you can write that this will be true only when sin kl is equal to sin n pi. So when you will compare both the side, you can write kl is equal to n pi, or k is equal to n pi upon L. This is our fifth equation. Now we have to put this value of k. Now we have to put the value of k into the equation number 2. What was the equation number 2? Equation number 2 was this one, this assumption, k square is equal to 2 me upon h cross square. Now put the value into this. So we know that we have written already k square is equal to 2me upon h cross square. So now substituting this value of k from here into this equation, and this becomes n square pi square upon L square is equal to 2me upon h cross square. So E is equal to this h n square pi square h square upon 4 pi square, and this is L square, 4 pi square, and to this. So 2 into L square into 4 pi square cancel out. So you are getting n square h square upon 4 to 8 and also this, and also in addition to the 2m 8m l square. So in general E n is equal to n square h square upon 8 n l square. So from this formula one can find out the energy of a single particle in an infinite potential well. So it is clear that E1 will be h square upon 8m l square. This is for n is equal to 1. For n is equal to 1. E2 is equal to n square, n is here 2, 4 h square upon 8m l square. This is for n is equal to 2 and this is equal to 4 times of E1. Now E3 will be n square h square, n is equal to 3, so 3 square 9 h square upon 8 m l square for the n is equal to 3, so this is 9 times of the ground state. And similarly one can find out for the 4 and so on. So E4 is equal to 16 h square upon 8m l square for n is equal to 4, and this is 16 times of the ground state energy. So it means all the energy levels are discrete and these are not uniform. So if we draw the energy level in a potential box, one dimensional infinite potential well, this is x-axis, x is equal to 0 our origin, and this is L. So n is equal to 1, this is E1, n is equal to 1, n is equal to 2, that is E2 correspond to n is equal to 2. Then after the difference basically increasing more than 2 times, so we can imagine this is E3 for n is equal to 3 and so on up to here. This will be fourth state. So these are the discrete energy level, discrete energy levels of a particle in the infinite potential well, in the infinite potential well. So this was the discussion about the energy of the particle in an infinite potential well. Now we have to find out the wave function of that particle, of that electron inside the well. So for this purpose we have to use normalization condition, because we have the function is psi is equal to a sin kx, but we don't know, this is clear that this wave function is not normalized. So we have to make this wave function normalize using the condition, normalization condition, to make normalize. So what is the normalization condition? Normalization condition for any particle, wave function will be minus infinity to plus infinity mod of psi square dx is equal to 1. So now we know the limits. The limits in our case are x is equal to 0 to L mod of psi square dx is equal to 1. Now using the boundary condition of our problem, we can write this formula in this way. Now the second point is related to the wave function. So 0 to L integration mod of psi square dx is equal to 1, where psi x is equal to a sin kx, where k is equal to n pi upon L. From the earlier case, k is equal to this, k is equal to n pi upon L. So using this relation, this k is equal to n pi upon L. So this function becomes psi x is equal to a sin n pi x upon L. So we have to find out the value of this a using this normalization condition. So substituting this value of psi x into the above equation, it becomes 0 to L a square sin square n pi x upon L dx. Now this integration could not be solved directly, so this can be written as a square 0 to L. Instead of sin square n pi x L, we have to use cos 2x formula. Cos 2x is equal to 1 minus 2 sin square x. Formula is what? Cos 2x is equal to 1 minus 2 sin square x. So it means sin square x is equal to 1 minus cos 2x 1 by 2. So here a square by 2 0 to L, and instead of this sin square n pi x upon L, we can write 1 minus cos 2 n pi x upon L dx. So after integrating these two functions, one and second, this becomes a square upon 2, this is 0 to L 1 dx, and integration of this single number will be x. So limits are 0 to L minus this is cos 2 n pi x upon L, integration of this, and this will be L upon 2 n pi cos, that will be sin 2 n pi x upon L. limits are from 0 to L. Now we have to put the value of x is equal to 0 and x is equal to L here. So the result will be a square upon 2, this is L minus 0, L minus sine 2n pi x upon L. This will be sine 2n pi L upon L, that becomes sine 2n pi, and in second case 0, it becomes 0, sine 0 is equal to 0. So L upon 2n pi into sine 2n pi, x is equal to L, L cancel out, so this is 2n pi, and when you put here 0, so it becomes sine 0, that is equal to 0. So this L upon 2n pi sine 2n pi, yeah, this one result, and from here, and this is always equal to 1, this is equal to 1. So L is square upon 2 into L is equal to 1. Why? Because sine 2n pi is equal to 0. So a square by 2 into L is equal to 1, or you can write a square is equal to 2 upon L, or you can write a is equal to under root 2 upon L. So this is the required result of the normalization condition, from the normalization condition. And now our wave function, this one becomes, it will becomes psi x is equal to this, psi x is equal to under root 2 upon L, that normalization constant is this one, and sine k is equal to n pi upon L, so this becomes n pi x upon L. So your x is equal to under root 2 upon L sine n pi x upon L. So this one is the standard formula for the wave function, and one can calculate all the wave function for the particle. Now we can plot the graph between the wave function and the probability. So the first three normalized wave function we can plot here. One dimensional box, this is one dimensional box along the x-axis, x is equal to 0, and this is x is equal to L. So psi 1, this is 1, psi 1, second little bit higher, 4 times higher, this is psi 1, this is psi 2, and next one be psi 3, this is psi 3, and in case of the probability, this is n is equal to 1, ground state, n is equal to 2, n is equal to 3. So these are the names of the states into the one dimensional potential well for the electron. And now the probability we can write. So the probability behavior also here of the particle correspond to n is equal to 1. The maximum height this is correspond to that psi 1 square. This is mod psi 2 square, and one more here is psi 3. This is psi 3. N is equal to 2, n is equal to 3. So these things are correspond to the particle in a box.